All right. um, um, waiting, waiting for YouTube signal to come in. Waiting for YouTube today. Okay, something is happening. Volume. Waiting for YouTube
Very
today.
nice.
Okay, let me throw away my gum. Pah! Very nice. Very, very nice. I must admit. Okay. Today is a very special day in the history of the known universe. Today we're doing the second video. So last time we did the quantum mechanics 1A, birth of the quantum 1. Today we're doing quantum mechanics 1B, birth of the quantum 2. Okay. So the last episode, I still wanted to figure out the Maxwell Boltzmann distribution, derivation of that equation, but I find it too boring to listen to these lessons, so I'll have to wait. We'll have to wait with that. Maybe we'll come back to that slowly. Everything I watched was too boring. Anyway, let's watch it. Part two.
Towards this end, we need to consider the wave aspects of electromagnetic radiation. First, consider one-dimensional waves, such as a vibrating guitar string. The string is fixed at its two ends and cannot move there.
This is a guitar. So he was. It's difficult to tell. There's a bunch of images, but ultimately this is a guitar. This is a guitar string. So a guitar string. I don't know how it works. I think there's like a string inside, and it's wrapped with another string that wraps around it to give it more mass, so it vibrates slowly, I guess.
Such as a vibrating guitar
Oh,
string.
so this one is vibrating.
The string is fixed at its two ends and
This
cannot
one,
move there.
they're all.
In
Oh,
between, it can oscillate.
that's like slow motion. All right, so now he is discussing. I don't know why he's discussing a guitar string. How did we end the last
Welcome to quantum
episode?
temperature of a material. The particles making up. Now we want to see what the relation is between temperature and electromagnetic energy.
I don't even remember discussing this.
Will be inflated until it glows. The initially reddish glow becomes whiter with increasing temperature.
So this is like black body.
Suppose we have a box enclosing a vacuum, the sides of which are made out of some material at a temperature T. The charges in the material will be in thermal motion, and the box will be filled with radiation. The particles making up the box contain kinetic energy, and the radiation in the box contains electromagnetic energy. We've discussed the relation between temperature and kinetic energy. Now we want to see what the relation is between temperature and electromagnetic energy.
Okay, straightforward.
The string is fixed at its two ends and cannot.
So, so now we want to know the relation between the thermal energy and the radiation, the electromagnetic radiation.
To this end, we need to consider the wave aspects of electromagnetic radiation.
So this is the wave aspect of electromagnetic waves, I guess.
First, consider one-dimensional waves, such as a vibrating guitar string. The string is fixed at its two ends and cannot move there. In between, it can oscillate with a single bump at a certain frequency. It can also oscillate with a two-bump shape at twice the single bump frequency.
Yeah, it could. Yeah, so this is mode n equals 2 frequency, nu equals 2 nu naught. Okay.
Or with a three-bump shape at three times the frequency, and so on. We call
these are standing waves. Is the first one a standing wave? I guess the first one, yeah, these are standing waves. All three, these are all standing waves. Yep.
Each of these vibrations a mode of the string, and we index them by the number of bumps in the string shape.
Mm-hmm.
We can draw a number line and place red dots at the integers n equals 1, 2, 3, and so on, and
Mm-hmm.
each dot will then represent a mode.
Mm-hmm.
We use Greek letter nu, which looks a lot like a V, to
Mm-hmm.
represent frequency. The frequency of the nth node is n times some fundamental frequency nu 0.
Mm-hmm.
So the fifth mode oscillates with the frequency 5 nu 0.
I don't understand what he's talking about. The fifth node oscillates with the frequency nu equals 5 nu naught. What? The fifth? I thought the red dots is what's not vibrating. What's going on? Why do people make everything so confusing? I thought the red dot is where it's not moving. It's the node.
The number of bumps in the string shape.
Oh, the number of bumps. Oh. So this is a bump. 2, 3, 4, 5, 6, 7, 8, 9, 10 bumps.
We can draw a number line and place red dots at the integers.
So this is where the positive bump, negative bump, I guess. I don't know. He's not showing the bumps.
N equals 1, 2, 3, and so on, and
Mhm.
each dot will then represent a mode.
A mode? What's a mode? Like, I don't know what he means by a mode. I guess mode n equals 3, n equals 2, that's the mode, and n equals 1, that's the mode. And the frequency here, n equals 2, the frequency is the second. What do you mean frequency? What's the definition of frequency? Frequency of what? The frequency, like how many times per second this vibrates? So it's double? Who says? Why? Why is it double? Are you sure? Where's the derivation? Anything? What do you mean by frequency? Frequency of what? Frequency like per time? What is going
First,
on?
consider one-dimensional waves, such as a vibrating guitar string. The string is fixed at its two ends and cannot move there. In between, it can oscillate with a single bump at a certain frequency. It can also oscillate with a two-bump shape at twice the single bump frequency.
How do you know? What's your evidence for that? Are you gonna show how you got the answer? Why would it be double? Where's the equation that describes this number? And like, give me something.
Or with a three-bump shape at three times the frequency, and so on. We call each of these vibrations a mode of the string, and we index them by the number of bumps in the string shape.
Is a positive and negative? Are these two bumps, or the bumps? This is 1, 2, 3. Yeah. So this is 3. So it's positive, negative, positive. So a negative bump and a positive bump are two separate bumps. Okay.
We can draw a number line and place red dots at the integers n equals 1, 2, 3, and so on, and each dot will then represent a mode. We use Greek letter nu, which looks a lot
Each dot represents a mode. Okay, I can live with that.
like a V, to represent frequency. The frequency of the nth node is n times some fundamental frequency nu 0. So the fifth mode oscillates with the frequency.
So the fifth mode oscillates with the. What do you mean? Oh, this is the mode number. I don't get it. I don't know what is this. What this is n, but what are you trying to say here? I don't even know what you're trying to say. I don't know what you're trying to say. Jesus help me. What are you trying to say? That what? For mode equals 1, what? You're not saying anything. There's a dot. For mode equals 2, there's a dot. I don't get it. What are you saying? And what is this? And what are you trying to say? Where's the information? There's no information here. My God.
5 nu 0. An important question for us is this. Within a given range of frequencies, say between these blue lines, how many modes are there?
Within a certain range of frequencies, How many modes? One. Between these two lines, there's only one mode. These cannot survive. It's only integer number. You can't have 4.5 because the half means it's moving, but we said it's tied at the end, so it can't. For a one-dimensional wave, the density of modes, number of modes per unit frequency range, is constant. For this range, it's 1. For this range, it's 5. I don't know.
For the one-dimensional case, we see that the so-called density of modes is constant. If we move the blue lines to the left or right, we'll, on average, get the same number of modes between them. We express this as Greek letter rho of nu equals a constant a.
Mm-hmm.
Now consider two-dimensional waves, such as on the surface of water or a vibrating membrane.
Mm-hmm.
A membrane fixed at its perimeter can vibrate with one bump at a certain frequency, or two bumps with a higher frequency.
Mm-hmm.
But there are two ways to have two bumps, so we can have two different modes with the same frequency.
Mm-hmm.
And in general, we can have any number of bumps n in one direction and any number m in the other direction. So the modes are now represented as number n.
I got lost.
And in general, is to have two bumps, so we can have two different modes with the same frequency. And in general, we can have any number of bumps n in one direction and any number m in the other direction. So the modes are now represented as m in the other direction.
What are you trying to say? I don't get it. So node n equals 1. Is this right? N equals 1, m equals 1.
A membrane fixed at its perimeter can vibrate with one bump at a certain frequency, or two bumps with a higher frequency. But there are two ways to have two bumps, so we can have two different modes with the same frequency.
Two different modes. I guess these are modes. No, this is the mode. But this is also... He's reusing the word mode. This is incorrect. This is frequency. Wait a minute. This is not n equals 1. This is n equals 2. And there's m equals 1 and m equals 2. This is n equals 2. And this is n equals 2. This is incorrect. This is a mistake. So 144, n equals 1. That's not the right mode. Or unless m... Oh, wait, what? I'm lost. I don't know how he's counting anything. Here there's 3 bumps. So m is the number of bumps. And n, what is n? The mode? I don't know. Like, how am I supposed to understand this? I'm supposed to, he's hinting and I'm supposed to learn everything on my own. Like, I'm supposed to develop quantum mechanics on my own. Thank you. Thanks for not helping.
Or a vibrating membrane. A membrane fixed at its perimeter can vibrate with one bump at a certain frequency, or two bumps with a higher.
So this is the higher frequency. Is n the frequency? And now we're going to have m equals 1, m equals 2 for n equals 2.
Higher frequency.
For n equals 2, still m equals 1.
But there are two ways.
M equals 2, but why is he saying n equals 1? What I don't understand. Anyway, okay, so he has a mode, but n is the mode, m is the direction. I don't know. I mean, I don't know.
Is to have two bumps, so we can have two different modes with the same frequency.
Where's the frequency here? Is it n? It says here mode n, or is this the mode? Where's the frequency? Where's the mode? It can't be n1, so it must be this is the frequency. It can't be because, again, m is 1. So this can't be the frequency because there's 2 bumps. But there's 2 bumps here. And there's 2 bumps here. So m is the frequency? Or the mode, I'm sorry. So what? I don't understand this. Well, what the heck is going on here? How many comments? 54 comments. You see. Yeah, this is very old, yet very few comments, but probably a lot of views. Yeah, 54,000 views and 54 comments. So one comment for 1,000 views, sure. And everyone understood this part, of course, because it's so clear. He's totally not contradicting himself. Let's see. And what is new with a zero value? What is the value of constant A? Someone may ask, what are modes? Modes are components of the wave. Any electromagnetic wave can be expressed as superposition of those modes, but why the frequency is always proportional to the inverse of the wavelength? It is because the electromagnetic wave propagate at the speed of light, hence we have, I don't know, mind equals blown. In the previous 1A video, it was mentioned that the Boltzmann distribution was P is equal to 1 over K, blah, blah, but here you mention it as this. Later is mentioned as this. Does A here? Anyway. When you talk about the oscillating membrane, you use concept of fundamental frequency, same as in the one-dimensional case. When I look at the video, I see two orthogonal frequency components in modes n equals 1, m equals 2, and n equals 2, m equals 1, but cannot get a sense of the frequency of a particular mode. What is the formula as it is? I refer to the formula at 203. Ines. It is due to the form of the wave equation that governs the behavior of the membrane. We discussed this a bit in video 5A. Wonderful. Although not to the level of detail of deriving the formula you asked about. Basically, it's because frequency squared appears in the wave equation. When you have oscillations in 2 or 3 dimensions, each dimension contributes a squared something to the squared frequency. You take the square root of... Okay, I want to kill myself. I'm not able to understand what you mean by density of modes. Please clarify. Are there any series of videos starting with classic mechanics or maybe... Okay. When the value of the constant A is evaluated using the condition that yeah, people say, oh, there's free content on YouTube. Yeah, that's it. But like if you go to college, I don't think you'll get a better I don't think you'll get a better understanding. You're still going to have to figure everything out on your own, because at the end of the day, people don't explain. Like the explanations, for some reason, I don't know, there must be some universal law that forces all lectures to be incomplete. Yeah. We should create like an incompleteness lecture theorem. All lectures are always incomplete for some reason. You always have to kill yourself trying to understand what the heck is going on. Oh my god. Can you explain how the corresponding frequency is proportional to the square root? Oh my god. Like others below, I have trouble with the 2D formula. I'm not even up to the formula. So interesting. Don't know if you're aware of a late paper from Poincaré showing that Planck's law. Okay. I love you, man. Nice video, but it did not explain why do all modes contain equally energy. Why is it so? Just as expected, it doesn't get easier. Oh well, more brain lubrication required. Yeah, these lectures are a great complement to David Bohm's quantum theory. It might be a good thing to mention that the wave is a standing wave. Okay, this was truly helpful. Minor correction of vibrating guitar string. That is, it doesn't vibrate in one dimension, i.e., up and down or left and right. It rotates around its axis or rest position circularly. Really? I have to say, your channel is quite good. Fantastic, brilliant. This series on is absolutely your video. Is there a specific expression or statement that aren't clear? I'm glad. Okay, I'll try to explain some of the concept as we go along. My God, I'm gonna kill my. I don't know if I'll be able to understand this. This is from 12 years ago, and nothing has been clarified in the comment sections. I don't know what to do. I don't know what he means by mode, by N and by M, and by mode. I just don't know. I don't know what is N and what is M.
Or a vibrating membrane. A membrane fixed at its perimeter can vibrate with one bump at a certain frequency, or two bumps with a higher frequency. But there are two ways to have two bumps, so we can have two different modes with the same frequency.
So maybe what he says is, I don't know. I don't know.
Two ways to have two bumps, so we can have two different modes with the same frequency. And in general, we can have any.
Okay, N equals 2, meaning I don't know what. M equals 3. I don't know. I don't know what he means.
So we can have two different modes with the same frequency. And in general, we can have.
This is M equals 3, N equals 2. I don't know what he means by these things. So 3. How many ways can you have 3?
Any number of bumps N in one direction and any number M in the other direction.
Did he show the two directions? I have no idea. And now he's gonna put it in some graph? What?
So the modes are now represented as points on a two-dimensional grid, indexed by two.
I have no idea what this says.
Two numbers, N and M. The corresponding frequency is a fundamental frequency, nu zero.
He's just asserting. No, he's not deriving any equations. I mean, this is just an assertion. So this is not going to. You can't. You. This is not a course. This is nothing. This is nonsense. I don't know what N and M are. I have no idea. Like one, when there's two what? You can have 2 and 8? What is 2 and 8? I don't know. I honestly don't know. How can you have like 3? I don't. You can have what? I don't know what this means. What is N and M? He doesn't. I don't understand. I'm wasting time.
Times the square root of N squared plus M squared. This is constant on a circle, so a range of frequencies corresponds to the area between two circles. At higher frequencies, there will be more area, hence more modes for a given frequency range.
What is going on? I don't know.
So here, there will be more modes with frequencies between 7 and 8 nu zero than between 2 and 3 nu zero. For two-dimensional waves, the density of modes is proportional to frequency, and we write rho of nu equals A times nu.
I don't know what he's talking about. He must be reading from a textbook where he's skipping over sections and just giving us some conclusions. I don't know. I don't know.
Finally, we get to three-dimensional waves, such as the oscillations inside a microwave oven. These are a bit harder to illustrate. The bumps now correspond to cubicles inside a larger volume. We could, for example, divide the volume into two regions in one dimension, three regions in a second, and four in the third. So our modes are now indexed by three numbers, n, m, and l. Each mode is a point in a three-dimensional grid, and a given frequency represents a spherical.
Every time I stopped, it's just that my fingers slipped as I fell asleep. I'm just falling asleep. I'm just trying to figure out what the heck is he talking about? Like, he's not explaining anything. He's just asserting. I don't know what he's not even asserting. I don't know what he's talking about. This is terrible explanation.
Surface. The density of modes now corresponds to the number of grid points between two spheres. This is proportional to the square of frequency, and we write rho of nu equals a times nu squared.
No idea.
The reason this is important is that we would expect each of these modes to act like an energy container, similar to molecules, with an average energy of Boltzmann's constant K times
No idea.
temperature T. Since the number of modes increases as the square of frequency, we should then expect, for a system in thermodynamic equilibrium, the intensity of radiation to increase with temperature and as the square of frequency. That is, much more radiation at higher frequencies. This is the prediction of classical physics, called the Rayleigh-Jeans law. We write the intensity of radiation as U of nu equals some constant A times nu squared times K times T. This is often plotted using logarithmic scales, in which case it forms a straight line. Let's see how this stacks up against observation for the largest box we know of, the universe. Here we have the intensity of the cosmic background radiation, the afterglow of the Big Bang, versus frequency. The points with error bars are observed values, and the line is the Rayleigh-Jeans law. The agreement is excellent, at least for the range of frequencies shown. In general, this law accurately describes what is observed at low frequencies. We see that it cannot be true in general, however, by continuing to follow the line to arbitrarily high frequencies. At infinite frequency, we would have infinite intensity. Not good. This dilemma is sometimes called ultraviolet catastrophe. Fortunately, this is not the way nature works. As frequency increases, the radiation intensity reaches a peak and then rapidly drops off. Convenient for us, but why does this happen? High-frequency radiation, ultraviolet light, X-rays, gamma rays, certainly exist, and the density of modes argument is sound. We are forced to conclude that something is keeping the high-frequency modes from absorbing as much energy as the low-frequency modes. But what causes this?
There's just all he wants to say is that there's just more modes of oscillation with the higher number of nodes and the higher dimensions. When you add, like in one dimension, it's 1-to-1. You add a node, that's it. The energy is linear, let's say. But in two dimensions, because of the halfway theorem, what do you call it? Anyway, there's just more modes of oscillation. Because there's more modes of oscillation, and every oscillation is possible, so in two dimensions, you just the more nodes you have, the more bumps you have, right? For each combination, for each number of bumps, you must have an equal amount of energy. There's no reason for the energy to get dispersed. I would say, why would in order to vibrate with so many nodes, like it's less likely. You want to tell me that it's as likely, and actually it's like more energy is absorbed, quote unquote, by the higher modes than by the lower modes, because there's more ways to vibrate. But it's very unlikely that the system will vibrate in anything except for the first mode. Why would the system suddenly vibrate in the second, the third mode? Systems are simple. They only end up vibrating in the first mode. Like you plug a guitar string, it only vibrates in the first mode. It doesn't suddenly switch to the second mode, to the third, to the fourth, to the fifth, to the sixth, to the seventh. It doesn't just switch.
Waves, such as on the surface of water or a vibrating membrane. A membrane fixed at its perimeter can vibrate with one bump at a certain frequency, or two bumps with a higher frequency. But there are two ways to have two bumps, so we can have two different modes with the same.
So you want to tell me, let's say a system could only have either mode 1
Can vibrate with one bump at a certain
or
frequency,
mode
or two bumps
2.
with a higher frequency.
But mode 2 has two sub modes.
But there are two ways to have two bumps, so we can have two different modes with the same frequency.
So he calls it modes. He confuses modes and frequency. So this is, let's call this the second frequency, but there's two modes. M is modes. It doesn't matter. Forget about his numbering system. So he has, what he wants to say is, let's say there is a system that could either vibrate in the second frequency or in the first frequency. But in the second frequency, it can vibrate with these two bumps or two bumps in this direction. So the system can vibrate in three ways: either one bump going up and down, or two bumps where the first one is closer to us and the second one is away from us, or again two bumps where the first one is on our left and the second is on our right. Right? So there's three ways that the system can vibrate. So you would say, oh, statistically speaking, probability speaking, all three are just as likely. So when it comes for the system to vibrate, the amount of energy that is invested in each mode is equal. This is the equipartition theorem. He doesn't bring it up. I don't know why. But according to the equipartition theorem, that's the great theory that they had. The ultraviolet catastrophe is based on this theory. It's based on this prediction. Oh my god, I'm falling asleep. Okay, I gotta go. My brain is shutting down. I gotta go. This is I think I'm beginning to understand. I'm beginning to understand what he's trying to say, because I've seen many lectures about the ultraviolet catastrophe, and I don't know how convinced I am that there is an ultraviolet catastrophe. So we'll come back to the ultraviolet catastrophe next time. So we'll stop here. Let me see how long we've been here. We've been here for 34 minutes. It's bad enough. Maybe I'll put a link to today's. No, we can't put a link. Links are not allowed. We'll come back to it next time. All right. We'll stop here. Bye.